Hello and welcome to the Hydrate Transportation Modeling with LedaFlow webinar, and thank you for accepting the invitation. My name's Mike Branchlower. I'm the Strategic Sales Manager for Production inside Kongsberg. If you're having any problems with audio, please go to the audio pane and click on Sound Check in blue. I've also put that into the chat, but if you're having problems with audio, you will not have heard that anyway. Okay. You'll have the opportunity to submit questions, so please just type them into the questions panel that you can see on the right-hand side there. So please send them in at any time. We'll answer a few as we go along, but most of them will hold until the end of the presentation. Please also note there's a LedaFlow product sheet that you can download as well in the handouts pane. I'm now going to hand over to Wouter Dijkhuizen. He's the LedaFlow product champion, and he's going to present and demonstrate hydrate transportation modeling with LedaFlow.
Thank you, Mike, for the introduction. So this webinar is about hydrate transport modeling in LedaFlow. So the contents of the webinar are first a very short introduction about why we are interested in doing this. Then we'll go through the technical details of the hydrate transport model, a little bit about the background and some implementation details. And then finally a live demonstration of what this looks like in LedaFlow 2.5. So first of all, most of you will probably know about hydrate formation. So this is a big issue in most oil and gas production systems. So typically in colder climates, this may already be a challenge, or this is normally a challenge in even during nominal production, even without doing any special operations. But even in warmer climates, it can be problematic. For instance, during the opening of a well choke, then temporarily you could get low temperatures and hydrate formation. So this is something that most flow assurance studies at least touch upon. So typical preventative measures for hydrate prevention are pipeline insulation, chemical injection, which includes mainly glycol injection, and also active heating of the pipeline. So these preventative measures, they add cost, not just during the design and building of the system, but also cost while using them, for especially the chemical injection. And they're typically designed very conservatively. So then the question is, what happens if we allow hydrates to form? And that is the main driver behind developing the hydrate transport feature in LedaFlow. So the objectives that we have, the primary objectives are to study the production and other typical operations with some limited hydrate formation, as opposed to being really conservative and avoiding hydrate risk everywhere and all the time. But at the same time, we do not intend to simulate full pipeline blockage. So we don't want to go too far. So we're just interested in a limited amount of hydrate formation that is still possible to operate safely with. Then also we want to simulate the effect of hydrate formation on the pressure drop in the production system, mainly because that will, if the pressure drop in the pipeline goes up, probably the wells will produce less. So that is important to take into consideration when determining if it's feasible or not. So the effects there that we're looking at are higher liquid viscosity due to hydrate particles, which means more friction. And also during the hydrate reaction, water and gas are being consumed. So in principle, it's also possible to end up with less friction and a lower pressure drop because mainly the gas is transported as hydrates, taking up less volume, giving less pressure drop. And then secondary objectives. So we also want to simulate hydrate remediation strategies potentially. So what we're doing here, it should be compatible with having thermodynamic hydrate inhibitors and also pipeline heating. Some of the assumptions in the model. So especially the sticking of hydrate particles to the pipe wall, it's extremely difficult to accurately predict the physics of that process. So that's why we didn't include that. So basically what we're assuming is that the hydrate particles, they do not stick to the pipeline because we can't predict this properly. And similarly, we also assume that hydrate particles do not grow too large. So again, that it's very difficult to predict that properly, especially because LedaFlow does not know the details of the chemistry of the production system. So we would have to know in detail what the oil consists of, etc., which is not feasible for these kind of simulations. And also assuming that the hydrate particles do not grow too large is it's consistent with using anti-agglomerants, which could be naturally occurring in the oil or artificially injected into the system. So that's something to take into consideration. So basically the hydrate reaction that we have in the hydrate transport model that is giving us the hydrate particles. So that's basically converting hydrate former, which is normally gas, but it could also be dissolved gas in the oil, and water. Those are being converted into hydrate particles. So the main driving force here is the hydrate temperature margin, like what you're used to when doing hydrate risk assessments, and also the surface area of the hydrate particles, taking into account the inhibitor concentrations as well in the hydrate temperature margin. So that is shown over here. This is the expression for the mass transfer term. You can see the temperature, the hydrate temperature margin is shown in red here, which is based on the hydrate curves that we define. And the surface area that is defined, that is based on the size of the hydrate particles and the volume fraction of the hydrate particles. So another important aspect of this mass transfer term is that it will stop when we run out of either hydrate former or water. And this is crucial for preventing for making sure that we don't overestimate the hydrate risk. So there may be a driving force for hydrate formation, but if we run out of water, we would like the reaction to stop so that no further hydrates are formed. And also the reaction is reversible, so it is possible to dissociate the hydrates again, for instance by heating or by adding inhibitors. When we have formed hydrate particles in either the oil or water phase, then we need to do something with the liquid viscosity, because that will increase due to the presence of these particles. And for that we have some slurry viscosity models. The default one is the Thomas model, which is a Newtonian model, so it's not dependent on the shear rate. So this model only depends on the volume fraction of hydrate particles, and you can see in the plot to the right what this does to the relative viscosity of the liquid. So if you have a reasonable amount of hydrate volume fraction, it quickly increases the relative viscosity. And then there's also a more advanced model, that is the SOFA model, that was devised by Total. And that one is non-Newtonian, so it also takes into consideration the shear rates in the flow. So you would need to do some lab experiments to find the parameters of the SOFA model. But on the other hand, the Thomas model, it already comes with reasonable default parameters in LedaFlow. So some of the other model details. So the hydrate particles, they can form in either the oil or water phase, or if you really want to, you can also let them form in both phases, but that is kind of unusual. So whether or not the hydrate particles form in the oil or water phase, that mainly depends on the wetting properties of the hydrates. So if you have surface active molecules in the oil, then basically this would promote oil wetted hydrates. And in the absence of such molecules, hydrates would be preferably water wetted. And it's not possible for LedaFlow to know this effect, so that's why we made this a user input, and it's possible to change this distribution coefficient y, which is shown on the right in these formulas here. I will demonstrate that in the demo later too. And then the second point, the reaction heat is modeled. This is very important. So when hydrates are formed, the enthalpy change associated with it will limit the hydrates formation, because you will need to remove more heat from the system in order to get hydrate formation. So this is an important aspect of the model. And then finally, we have a stop criterion in this model, which will stop when a user-defined limit is reached. So the hydrate volume fraction, it is normally the standard stop criterion. So by default, it's set to 50%. So that will mean that as soon as we have a local volume fraction of 50% hydrate particles, then the simulation will stop. Alternatively, you can use a stop criterion based on the liquid viscosity, so that when the viscosity gets too high, then the simulation is also stopped. So the main purpose of this stop criterion is to alert the user to any possible hydrate blockages. So we don't know exactly when the hydrate blockage occurs, but this is just to be conservative, basically. Okay, then we go to the live demonstration in LedaFlow. So I will convert an existing pipeline model to use the hydrate transport feature, and also demonstrating the heat transfer limitation. And then also at the end, I will compare this simulation to one with an uninsulated pipeline, which will show the stop criteria. So this is LedaFlow 2.5. It is the model that I've prepared here for the base case is basically a simple single pipe case consisting of a flow line and a riser. You can see that the flow line is approximately 10 kilometers long. There's some small undulations going up and down, and then there's a roughly 300 meter tall riser at the end. So this is a very typical case where we produce subsea and then go all the way to the top of the, go to a platform. Okay, so I can copy this case so we can turn it into a hydrate transport case. So I'll call this one insulated. Yep, so now the case has been duplicated, and then we can turn on the hydrate transport feature. So the first thing we need to do is add a hydrate curve to the PVT, because this hasn't been done yet in the base case. So in order to do that, I'm going to the hydrate curves. Yeah, and then over here in the hydrate curves manager, I can add a new hydrate curve. So the default curve that I'm adding to the case, it's using the Hammersmith formula to account for hydrate inhibitors. This is not important here because the simulation, it does not inject any hydrate inhibitors. So whatever I choose here, it doesn't really matter. But by default, LedaFlow, it takes into consideration any kind of hydrate inhibitor that might be present in the case. So this is quite nice. So LedaFlow can have, for instance, it can use methanol as a hydrate inhibitor, and at the same time also take into account other hydrate inhibitors like glycol, or even the presence of salts. The default curve, it's already, it looks reasonable. So we can see that this is quite typical. So normally for a simulation, you would make your own hydrate curve using PVD software, but we'll skip that in this demonstration. Okay, now I've made a hydrate curve. We just need to associate it with the PVD table. So I'm selecting the default curve here for this table, and I'm just applying it here. Then the second step is to turn on the hydrate transport. So if I put this to yes, and then go to the settings. So these are all the main settings for the hydrate transport feature. So we're not going to change all of this except for one setting. I would like my hydrate particles to end up in the water phase. So that means I'm setting this hydrate distribution coefficient to 0, which means that none of the hydrates will end up in the oil phase, which means 100% in the water phase. Okay, so I'm just applying these changes, and now it's saying that custom fluid tracking was enabled and hydrate transport was enabled. So this is good. So the custom fluid tracking is used to track the hydrate particles through the pipeline, and also the hydrate former. Then the third step in order to make this simulation run is that I will have to put in some hydrate former at the inlet. So LedaFlow needs to know how much of the inflow into the pipeline can be converted to hydrates. So that is this hydrate former fraction over here. So it's possible to estimate this by summing together the total fraction of methane, ethane, propane, and also CO2 in the flow. So this information is available from the composition that was used to make the PVT table typically. So in this case, I will use 30%. And that is basically it. So this is sufficient definition to run this case. So I'll just initialize and run it now. So I'm running the simulation for 2 hours. Yeah, so it was initialized very quickly and now the simulation is running. So we don't need to wait for the simulation to be done in LedaFlow. We can already proceed with the analysis, at least making some plots. So we're using the hydrate transport plot template to look at the results. And then we can already see some results. And in the meantime, the simulation has now completed. So these are the results from the simulation. We can see that the hydrate temperature margin, it goes from a negative number, which means that we're above the hydrate formation point. It's going to 0, which is where the hydrate reaction will occur. And then after that, it's hovering close to 0, which means that the hydrate formation is occurring here. We can also see that by plotting the volume fraction of the hydrate particles. We can see that after this point in the pipeline, we're slowly forming more and more hydrates along the pipe. And this reaction, it never really finishes because this pipeline is insulated. If the pipeline were much longer, then maybe at some point we would reach the end where all the water is converted, but not in this case. There's still a little bit of water left at the end. So the reaction is not complete. So what we can learn from this is that basically in this case, the hydrate formation is limited by heat transfer because it takes a while, so it's not reaching complete conversion of everything into hydrates. Okay, then it's interesting to look at the other possibility, which is when heat transfer is not limiting the case. So we can do that by duplicating this case and turning it into an uninsulated pipeline. So I'm taking the same case with only one modification. I'm changing the wall definition so that there is no insulation on this wall. It will only consist of a steel pipe. And then I'm running the case again. Yep, the plot is still here because we've duplicated the other case. And here we can see what is going on. The hydrate reaction, it's occurring much sooner in the pipe because there's much more heat transfer. And we can also see that the simulation, it actually stopped. That is because of the stop criterion that we've used. We can see that here in the output window that this is a controlled stop due to a possible hydrate plug. And that is because we formed 50% hydrates at this point in the pipeline. So LedaFlow is telling me that we have a potential problem at this point in the pipe, which is correct. We have 50% hydrates here, and all the water is converted into hydrates at this location. So it's going to be very difficult to transport this. So we don't really want to operate in this way. So this is just showing the difference between an insulated and an uninsulated pipe. And this hydrate transport feature, it can be used for many other studies as well. So I'm handing it back to Mike now to answer some questions.
Okay, very good, Wouter. Thank you for that. Yeah, we have a few questions for you. So I'll read them out and I'll type in the answers as we go along. So apologies if you hear a lot of noise. I'll type as quietly as I can. First question, mass transfer rate calculations, a constant hydrate particle size is considered. Is that a realistic assumption?
Very good question. I will just go back to the formula. So basically, the way this reaction is built up, we are indeed assuming a constant particle size. So this is kind of an average particle size. That's how you should interpret this. But what I can say about this is that maybe in reality it should not be constant. But at the same time, this surface area, it doesn't really matter during the reaction, because normally the hydrate formation, this reaction rate is so fast that it doesn't really matter what the kinetics are. It's yeah, it will basically be the same if you change this this diameter, because normally for hydrate formation, it will either be limited by the heat transfer, or it will be limited by the amount of water that is available for this reaction anyway. So in my opinion, the kinetics are not that important for this kind of calculations.
Okay, very good. Next question. Just send this one to all. Is the hydrate volume fraction relative to the pipe volume or the volume of the water phase?
It depends. So the one I've shown in these plots over here. So this is the volume fraction. It says volume fraction total water. No, that's not the right one. So sorry. So the hydrate volume fraction over here. This one is compared to the total pipeline, but it's also possible to plot the hydrate volume fraction relative to the water phase in which it's located.
Okay, so the answer is really both then in that case. Good.
Yeah, but in the plot template, it's showing the relative to the total volume of the pipe, which is more reasonable, because then you can compare it against the stop criterion, which is defined in a similar way.
Okay, so I'm just going to enter this, but default is volume of. Okay, next question is, and we'll take questions until 3:30, and if we don't make it, we'll have to get back to you separately. I think we know the answer about how is hydrate deposition handled. I mean, we don't model hydrate deposition, I guess is the answer to that one.
Yep.
We are not.
Yeah, that's just one of the assumptions of the model.
Yep. It's just formation and transportation. Okay, sensible. Next question is, tau in the SOFA model is the shear question mark. If so, what shear? Wall, local shear, interfacial?
Yeah, that's the wall shear stress.
Okay. Okay. Is free water required to form hydrate? Free water or any water? I guess that's, I don't.
Yes, so we need free water in order to form hydrates. So theoretically speaking, you could form hydrates also from water vapor in the gas, but yeah, I think from what I understand, this reaction is extremely slowly. So I don't think that would necessarily be a flow assurance risk.
Okay. So I'm just sending something.
And at the same time, you need a lot of water to form a significant amount of hydrates, and I don't think a little bit of water vapor is enough to really produce a lot of hydrates. For that you really need free water.
Yeah. If we want to use a non-Newtonian model, what type of experiments are required?
Yeah, so this will basically be lab tests at different hydrate volume fractions, and then the typical kind of rheology test with a Couette cell. So it's just like characterizing drilling mud, probably.
Yeah.
But you will have to pressurize it in order to keep the hydrates alive, I guess.
There's some discrepancies or some discussion here about the first answer. Hydrate formation also depends on mass transfer considerably. Well, and kinetic is important. So what did we not say there? The first question was related to mass transfer rate calculations and the constant particle size. So what we were saying is that's an average size, and if you change the size, it doesn't make a big difference. But
no, that's basically what we've seen. I've actually done those simulations looking at the effect of the particle size, and that technically there's a difference. But what we see is if you change the particle size, only this initial bump here where the hydrates start to form, this part will change, and not really the end here. And the reason for that is that this is kind of this reaction is kind of a first order reaction. At some point you have so much surface area that adding more surface area doesn't really matter. And then the reason why it doesn't matter is because the kinetics that we have by default here in LedaFlow, they're so fast that we have plenty of surface area to run the reaction. So we just need to have a little bit of nucleation, and then it will be very fast.
Yeah, but we're not saying hydrate formation doesn't depend on mass transfer, are we? We're just saying the
yeah, so theoretically it does, and in practice probably also a little bit, but it's not very significant, I would say. It's not the most important thing. I think the most important factor here is heat transfer.
Okay. Fine. Does the amount of hydrate former have to include components in the liquid?
Yes, so this hydrate former fraction, it is compared to the total inflow, so that's all the phases. So basically what you can do is you can take the total composition of the inflow that you also use to make the PVT table, and you just lump together the components that I talked about.
Okay.
Basically all the light components.
Which case might be the worst case scenario? 100% hydrate in water, in oil, or in a mixture, or in between? Not sure what the.
Yeah, that's impossible to answer. It's you would have to do the study, but basically you cannot choose if the hydrates form in the oil or the water. That's just a given basically with your chemistry. So if you have a certain kind of oil, then you will end up in one situation, or maybe with gas condensates you will end up in the other situation. So you can't really design that.
Yeah, so you need to do simulation. Yeah.
And then whether or not the hydrates they end up in the oil or the water phase, you can determine that in the lab.
Yeah. Okay. So I'll try and run the best I can. When we're in and out of the hydrate region, does the formation stop and start again? So I think you've covered that already, didn't you? Saying how it.
Yeah, it's fully reversible.
Yeah, you said it can melt or dissociate. Yeah. Yes, it is. That's good. Okay, another 1 or 2 minutes to go. Thank you for all the very good questions. How do we have provisions to handle Joule-Thomson effects in gas condensate pipelines, and how that would affect sort of hydrates and wax?
Yeah, so LedaFlow can handle Joule-Thomson effects, and then that can be used with the hydrate transport model too.
Okay, so that's yes. Let's do that. So next question. You can answer the next question in more detail, but do we have any examples about how it's calibrated with data from fields? But we don't have any field data is one of the challenges. So if you have any field data, we'd love to get it, but it's not readily available. I suppose that's the answer, isn't it?
Yep.
Yeah.
And if there was field data available, then maybe people wouldn't really share it because it's kind of a disaster.
Mm. Okay, we're pretty much out of time. This is a good question, actually, and I know it's something we've been looking at. Is there a minimum subcooling required for nucleation?
Yeah, so this amount of subcooling that we need in order to get this reaction, that depends on the kinetics. But it's typically very small. Like in this case, you can see the subcooling is only a fraction of a degree Celsius.
Okay, so it's quite small. Okay. Cool. Can we do this with just a gas phase? We don't need an oil phase necessarily?
Yeah, so it works for any system. So you can have just gas condensate, or oil case. So you don't need a gas phase either. So it works equally well from the gas and the oil phase.
Yeah. Is there a viscosity increase if the hydrate is distributed, if all the hydrate is in the water phase?
Yes.
Okay. Okay. I'm just trying to get through. I think we've got like 1 or 2 more to go. So if you just hold on for another minute, we can do the questions. Benchmarking against flow loop data, not yet, is the answer to that one. Better, correct?
Yep.
Yeah. What's the limit for the maximum relative viscosity?
There's not really a limit, but at some point this viscosity will be so high that the pressure drop will be enormous, and then the simulation will stop. So I don't think the LedaFlow model is entirely validated for extreme viscosities resulting from the Hydrate particles. So I would say that maybe using a Hydrate fraction more than 50% is maybe a bit dangerous.
Are there any known limitations of this model? I mean, we've mentioned obviously that we're not looking at formation of plugs and sticking to the wall, but anything else? Anything we would say is a limitation in here?
No, not really. Nothing in particular.
I mean, it kind of works as designed, doesn't it? But it's not addressing some other issues potentially. So as I said, it doesn't address plug formation or walls. Okay. I think that's all we can do, and that is the last question. So thank you for the very good questions. Thank you, Wouter, of course, for a very good presentation and demonstration. And thank you for everyone for attending. You should receive a follow-up email within 1 day, and that will give you a link to view a recording of the webinar if you want to see it again. And if you have any questions, please don't hesitate to send me an email. On behalf of Kongsberg, thank you for joining the webinar, and we hope to see you at the next one. Enjoy the rest of your day. Goodbye.